All right, so ideally as we go through this study guide, this is also now the second or even third time that we've kind of reviewed this stuff. Either we've reviewed it on whiteboards or the first time that we learned it in class, and now we get to recap it again. So hopefully today, as I ask questions, I have a lot of input from the rest of you, just like letting me know the answers. That helps me know that we're getting it along the way. So yeah, for any of this, we should have our blue and yellow sheets out to reference, and you will be allowed those on the test tomorrow. So starting us out, we started the unit by learning about converting either from fractions to decimals or vice versa. This is all without a calculator, so that's where our decimal sheet comes in handy. What we're looking at is, we have 3 examples here. So every time we want to simplify the fraction and then convert it, if necessary, to improper fractions. So sometimes these fractions are really nice. We can just look at something like 3/5, and it's exactly on our decimal conversion sheet. So we just look, we find it, and we write it down. So what is 3/5 as a decimal? 0.6. Excellent. And that's it. We move on. That's all. It's kind of like a little scavenger hunt. Sometimes we get to a fraction, and that's not on our conversion sheet, but we could look at it and we could simplify it first, and then it probably will be. What could we simplify this fraction by? 2, exactly. So we can divide by 2, which means that the fraction that we're actually looking for is 3/8. And that one is on our decimal conversion sheet. So we can look at that, and it ends up giving us 0.375. Those ones aren't so bad. What we have next is an improper fraction. So for us to really convert that to a decimal, what is our first step that we have to do? Convert it to a mixed number, exactly. So we ask ourselves, how many times does 2 go into 11? 5 times. And what's the remainder? 1, so that goes to the top, and the bottom stays a 2. And now what we're looking for is we want to find 1/2 on our decimal conversion sheet. That will give us 0.5. But instead of writing 0.5, because we have the whole number 5 in front, we're going to write 5.5. And there we go, we have our decimal. When we do this, the same thing but backwards. Sometimes it is just as easy as find the thing on the sheet and write down the fraction. So we want to see, okay, where do we find 0.8 repeating? Yeah, we get 8/9, and that's our fraction. There's no simplifying to do there. If we have something like 0.5, this shows up a couple of times on our sheet. So we'll have either 5/10 or 4/8 or 3/6 or any of those. We want to pick the most simplified version, which is the one that's to the leftmost on your sheet. What do we find? 1/2, exactly. So there we go. Once again, if we have something with a whole number part, we're essentially just looking for this section on our sheet. So 0.16 repeating, what would that be as a fraction? 1/6. So this gives us the 1/6. And then just like we had over here where we had kind of this 5 hanging out in front, this 2 in front will be a whole number 2. But then we are going to convert it to an improper fraction. So our final answer will not be as a mixed number. So we go, okay, what is 2 times 6? That'll give us 12. Adding the 1 to that will give us 13/6. What do we think? Awesome. Okay, our next thing that we learned in this unit was number sets. So we went through kind of the natural numbers, the whole numbers, and the integers, either what's contained in those sets and what is the fancy letter that we use to represent it. All right. So do we remember what is the fancy letter that we use to represent the natural numbers? It's a big fancy N. Yeah. So somewhere in the N, put the double line just to show it's not just an N, it's a fancy N. And the natural numbers is the set of counting numbers, starting at 1. So if you started counting on your fingers, kind of what numbers would show up there. So 1, 2, 3, going on forever. We only have 10 fingers, but it's technically forever. Next up, we have the whole numbers. What's our fancy letter for the whole numbers? W. And the set of whole numbers is the set of natural numbers, so everything we had over here, plus 0. So instead of just 1, 2, 3, it'll be 0, 1, 2, 3. And then we get our integers, and we wish it was a fancy I for integers. That would be really nice, but it's not. What is the letter that represents integers? It's a Z, but make it fancy. So this is a set of whole numbers, so everything we had in there, but also their opposites. Really what it is just our number line up here. So far we haven't seen any decimals or fractions. So we have 0 in the middle, positives on the right, negatives on the left. There we go. So again, these are all of our like nicer numbers. No decimals, no fractions whatsoever. What we have next is our rational numbers, and that's where the decimals and fractions first are introduced. What is the letter for rational numbers? Q. But make it fancy. And so when we get to rational numbers, what it is, a rational number is any number that could be written as a fraction with an integer top and bottom. So it includes integers, terminating decimals, and repeating decimals as well. And essentially the question we have here is, can we make each of those things look like a fraction without changing the value? Because then we prove that it's rational. So for each of these, we're looking to write them as a fraction for all of these examples. And we have different rules depending on what we're starting with. So if we are starting with an integer, then we just take whatever that integer is and we put a 1 on the bottom. And then suddenly it looks like a fraction without actually changing anything at all. So instead of 5, we're going to have 5 over 1. If we have a terminating decimal, which just means a decimal like this one right here, where it stops after a certain number of digits, what we want to do is we will turn it into a fraction where the denominator is either 10 or 100 or 1,000 or 10,000 or 100,000 or any number of a 1 with some zeros. And we want to take this portion of it and put it as the numerator. At this point, we're getting rid of the decimal. It's no longer there because then it wouldn't be an integer top and bottom. That would be a problem for us. And then we say, okay, because we have 4 things on the top here, we're going to have 4 zeros on the bottom. But we can't just have zeros. Dividing by 0 in math is kind of illegal. And so we need the 1 to really show that we're looking at like a multiple of 10 of some sort. Lastly, if we have a repeating decimal, so that would be something with the line on top like this, it's the same idea, but this time instead of having a multiple of 10 on the bottom, we're having a collection of 9s. So either 9 or 99 or 999. And so we take the portion from the top. In this case, we do have a whole number 3 in the front, and we can just throw that in front. Then we take the portion that repeats, so the 0, 4. I typically like to write the 0 portion just to remember that it's there. Because what we want to do is we look at how many things do we have on the top. That'll tell us how many 9s we should have on the bottom. And including the 0 here, because it is a placeholder. So having 2 things on the top means we have 2 9s on the bottom. In a lot of these cases, we could potentially simplify it, but for these questions, I will not make you do it. So do not simplify. This is the only question in which I won't make you simplify it, and on the test, I will put it in all caps. I'll bold it, I'll highlight it or something, saying don't simplify these ones. This, for example, could be simplified quite a bit, but we're just not going to waste our time. Our goal here is just to show that it could be a fraction, and we've done that. Yeah? Yeah, so if there was like a 3 here, then we would put a big 3 here. Or if there was a 10, we would put a 10. Yeah, absolutely. Great question. Any other questions so far? To show that it's rational. Okay. Next up, we have our irrational numbers. So if rational numbers were the fancy Q, irrational numbers is the Q with the little apostrophe. It's called Q prime. It basically means anything that's not rational. So in this case, a lot of what we look at is square roots and stuff like that. So sometimes we'll look at this and we'll say, okay, could we simplify this into a nice number? Yeah, square root of 25, what is that? 5. If you haven't noticed yet, if you flip over your blue sheet, you'll see a lot of stuff about square roots on the back there. There's also stuff about cube roots and prime numbers, but if you want to check that out, you'll see some information back there. You can use that if you'd like. And this one shows up to say, okay, the square root of 25 is 5. Would we say that this is rational or irrational? Rational, but it's not a fraction. But we could write it as a fraction if we really wanted to. We don't have to in this case, but I will just say it's rational in the corner here. Okay, looking at the next one, square root of 51. Is there a number that can multiply by itself to give us 51? Technically there is, it's just a decimal that never finishes, and so it's a non-repeating, non-terminating decimal, which just means that it's irrational. So we can look at this one, and there's not anything else that we can do here. We can either write irrational, or we can do the Q with the apostrophe. Either way, I'm happy. But there's no way that we could simplify this into anything nicer. At least not yet. In grade 11 you can. Maybe not this one, but other ones you can. You'll see. Okay, if we have a fraction here, what we want to do is split the fraction or the square root to the top and to the bottom. So I'll often rewrite this as the square root of 36. Of course it is. Over the square root of 49. And then we can simplify each of those individually. So the square root of 36 is 6, and the square root of 49 goes on the bottom. And is it rational or irrational? Exactly. So even though it looks like something that we don't immediately see on the back of our blue sheet as a perfect square fraction, or perfect square number, it simplifies nicely into something that is rational. And then lastly, a decimal. How should we approach this? Turn it into a fraction. And so we could see, does this show up as something that's nice on our fraction decimal conversion sheet? We do see this on our conversion sheet. Is this the same thing? Not quite, just barely not quite. That repeating symbol means it's different. And so this is where we want to use our skills from up here to say this is a terminating decimal. So we're going to take our 0.16 and we'll turn that 16 into the numerator. Because it's terminating, we'll have a 1 with some number of zeros on the bottom. Because there's two things on the top, we'll have 2 zeros on the bottom. We still have the square root symbol. And now we can say, okay, this is starting to look a little bit nicer. We can say, what is the square root of 16? 4. What is the square root of 100? 10. Oops, too many zeros. There we go. And could we simplify that? Yeah. They're both divisible by 2, so this actually gives us 2 over 5. In either case, it does show us that it's a rational number. What do we think? All right. As we get to irrational numbers, so something like the square root of 29 can't be simplified into anything nice. It would give us a non-terminating, non-repeating decimal. So what we want to do is estimate. And so for something like this, we're looking at what perfect squares lie on either sides of 29. And so we know that this would be between the square root of 25, which is 5, and the square root, the next one would be 36, which is 6. So we know that the square root of 29 is somewhere between these two values. So it'll be like 5 point something. We just want to be able to estimate to one decimal point to decide what it would be. And so for this, a number line is really helpful. So our number line will start at the square root of 25. So we'll put the square root of 25, which is really just 5. And then we are going to count out until we get to the square root of 36. I recommend not just putting the square root of 36 here and trying to evenly space it. It's almost impossible. But just say that, okay, we've got the square root of 25. So this would be the square root of 26, square root of 27, 28, 29, which will be important to us. So I'm going to bold that as a nice little dot. 30, 31, 32, 33, 34, 35, 36. Labeling either side there. And so looking at this right away, we see that it is closer to 5 than it is to 6. So it'll be closer to like 5.2 or 5.3 or 5.4. Another good strategy is to find the exact halfway point. So halfway between these two numbers. And we don't just want to eyeball it. We want to look at it and actually do some counting to say that we have 11 spots in here. And so halfway between those would be, well, 11 divided by 2 is 5.5. So if we look at 5.5 little tick marks over, that will give us to the middle there. So 1, 2, 3, 4, 5.5 would go right here. So this just helps us estimate even more to see, okay, well, if 5.5 is here and 5 is here, we're even closer to 5.5, so we can kind of start to gauge things a little bit more. I would say a good guess here would be something like 5.4. Just if I'm looking at this number here, I'm approximating that the square root of 29 is approximately 5.4. And if I type that into my calculator, I did it last block, we end up actually getting 5.389 or something like that. So it is a pretty great estimate just by looking at this line here. What do we think? Okay, can I get thumbs up, sideways, or down on the front page of this, just so I know who to kind of check into when we get to our practice test? Okay, cool. So flipping it over, we're going to do the whole study guide in one go, and then we'll get to the practice test, and you'll just have the rest of the block to do it. So the last couple of days, hey guys, thank you. The last couple of days we've been reviewing fraction operations. Sometimes decimals sneak into there, but mostly fractions. So when we're adding and subtracting, our main goal is that we have a common denominator. Sometimes we'll start out with a nice common denominator already. It makes our job a bit nicer. For example, here, it's already over 10. So we don't have to do anything to change the denominator at all. We just want to look at saying, okay, what is 4 plus 3? We get 7. And the important thing here is that we keep the denominators the same. Especially in the cases where we work so hard to make them match, we want our answer to match it as well. So in this case, it'll be 7 over 10. If possible, we'll simplify it. The one thing we don't ever want to do with adding and subtracting is pre-simplifying. So 4 and 10 could technically get smaller to be 2 over 5, but then we wouldn't have matching denominators anymore. So that would actually get us farther away from the answer. So this is it. Same idea. If we have matching denominators here, we want to double check what the sign is in the middle. This time we're subtracting. So we're asking ourselves, what is 3 minus 5? And so we will have some answers where kind of integer values, we have to remember what's happening. So we're starting at 3, we're subtracting 5. So that'll bring us to negative 2. And again, we keep the denominator the same. Am I done? No. What can we simplify by? Excellent. So we should get negative 1 over 3. And again, I don't really care if you have the negative sign on the top or in the front or even technically the bottom if you're feeling crazy. It's the same thing. So I'm just going to leave it at the top there. Okay. In both of these next examples, the denominators don't match. So we have to take our first step of making them match. And how we want to do that is by looking for the lowest common multiple. So what we're thinking is if we were to list out all of the multiples of 5, so 5, 10, 15, 20, blah, 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 and all of the multiples of 3, what would be the first thing that shows up in both of them? 15 would be our quickest one. 30 also works, but we would have some simplifying to do at the end. So here we're looking at our denominators being 15. And I often like to just set that up and say, okay, we're trying to make it 15s on the bottom. Because then we can ask ourselves, okay, how did we turn a 5 into a 15? Because whatever we did here, we'll have to do to the top as well. We multiplied by 3. So in order to turn that 5 into a 15, we multiplied by 3. So we have to do that up here, which means that we're going to have 3 times 1, which is 3 on the top. Same thing, we ask ourselves, how did we turn a 3 into 15? And we multiplied by 5. Which means that we're going to have 10 on top. And now that the denominators match, we can just kind of do the easy part, is we look at the tops and we say 3 plus 10 is 13. Keep the denominator the same. And there's no simplifying necessary in a question like that. So in this case, our lowest common multiple was really just multiplying those two denominators together. That's not always the lowest option though. So for something like 8 and 6, what would be the lowest common multiple? 24, exactly. So we're aiming to have both of these as fractions over 24. So again, I like to just set that up. Now we can say, okay, how do we turn an 8 into a 24? Multiply by 3, which means we do that to the top. So we have a 3 on top. How do we turn a 6 into a 24? Multiply by 4, which means we have a 20 on the top. And again, once we have matching denominators, we can do the easy part at the top. 3 plus 20 is 23. Keep the denominator the same. Can we simplify it? No, that's it. That's all. Move on. Okay, any questions there? Looking at the next ones, we have multiplying fractions. We'll kind of do it just the basic way here, and then we'll look at pre-simplifying in our next example. So multiplying fractions, we're thinking straight across. Which just means we multiply the numerators and we get a new numerator. We multiply the denominators and we get a new denominator. So 5 times 4 gives us 20. 8 times 7 gives us 56. And in this case, we didn't consider any pre-simplifying. But now we still have to simplify our answers. We ask ourselves, what could 20 and 56 both divide by? Yeah. Oops, why would I write a 5? There we go. And actually doing that, we'll get 5 over 14, I believe. Thank you. There we go. If we want to pre-simplify, we could have pre-simplified this one. We could have said this is divisible by 4 and this is divisible by 4. So we would have a 1 and a 2. And then we see right away that we would end up with 5 over 14. Sometimes you can choose whichever way you want to go. With numbers this big, we kind of have to pre-simplify, or at least I would recommend it. And so what we're doing here is we're picking one number from the top and one number from the bottom that are both divisible by the same thing. So just looking at these numbers here, does anything stand out as having factors in common? Yeah. 25 and 10. That's what I saw first too. So we see 25 and 10, and those are both multiples of 5. So we know that they can both be divided by 5. And so when we do that, 25 divided by 5 is 5. 10 divided by 5 is 2. So already we've knocked these numbers down to being quite a bit smaller. We can also go in and say, okay, is there anything else that we see as having factors in common? 33 and 9, what are they both divisible by? By 3. So we can divide by 3 for those ones. So 9 divided by 3 gives us 3. 33 divided by 3 gives us 11. And at this point, it's starting to get a little bit messy, so I usually like to rewrite it. So this is turning into 5 over 11 times 3 over 2. And we can go straight across now. We can double check that there's nothing else we could pre-simplify, and there isn't. So that means whatever we get as our answer is already kind of as simplified as it gets. So 5 times 3 gives us 15. 11 times 2 gives us 22. And we're done. There we go. The thing with pre-simplifying is it only works for multiplication. So we'll see in the next one that we have to be a little careful with when we use it for dividing. So this first one for dividing fractions, again, we're just remembering that the rules here are keep, switch, flip. Which refers to keep the first fraction the same, switch the division symbol to multiplication, flip the other fraction. And so I always write it out first to say, okay, this would turn into keep the first one the same, switch to multiplication, and then we're flipping this upside down. So instead of 6 over 3, it'll be 3 over 6. Again, for this one, we won't do any pre-simplifying. We'll do post-simplifying, I guess, just to see that it's an option. So 4 times 3 will give us 12. 8 times 6 will give us 48. And then what are these both divisible by? 4, also 3, which means that it is divisible by 12, and that will be our fastest way of getting to the final answer. If we divided by one of those other options, we would have just seen that there's still more that we could have done afterwards. So it's okay if you pick a smaller thing first, but what we get here is 1 over 4. Again, the 1 is super important to be on the top. Once the numbers get a bit bigger, we must wait until we switch to multiplication before we can pre-simplify. So pre-simplify does not work on multiplication, or sorry, on division. So we go through and we keep switch flip. So keep the first fraction the same, switch to multiplication, and flip that second fraction. And now we can look at what jumps out as being things that we could pre-simplify. 45 and 15, what are those both divisible by? 15, 5 works as well. If we do 15, it'll get us there a little bit quicker. So yeah, divide by 15, which is nice. That'll bring us to 3 with that one, and 1. It's always nice when we can get a 1 there, because it can't go any smaller than that. Is there anything else we could pre-simplify? 8 and 12, exactly. What are they both divisible by? 4. I'll bring it back at the end, if that's okay. So we get a 2, and we get a 3. And now looking at these numbers that are left over in my green and orange here, there's nothing else we can really do. So we're looking at 3 over 2 times 3 over 1, which now we can just go straight across to get 9 over 2. You might have pre-simplified different things. So 12 and 15 could pre-simplify.
I did 45 and 15, I did different.
Okay, yeah, you might have divided by 5 maybe. Yeah. And then you just would have had to maybe do a little bit more along the way. But we still get to the same answer. So there's no pressure in picking the biggest thing. It just gets you there a bit faster. And then our last ones are just a couple of questions here on like sneaky multiplication, I call it, and sneaky division. It's really just multiplying and dividing fractions, but looks a little bit hidden in how it's presented. So remember, anything to the power of 2 or with that's squared just means that we're taking whatever that is and multiplying it by itself. So here we're looking at, okay, this would be the same thing as 2 over 5 times 2 over 5. And there's no pre-simplifying we can do there, so we just go straight across, and we'll end up getting 4 over 25. Same thing with sneaky division. This one especially looks quite intimidating, but all it is whatever the top fraction is divided by whatever the bottom fraction is. So I really recommend just writing it out horizontally. So this is the same thing as 2 over 3 divided by 7 over 8. Anytime that we're dividing, we're really thinking keep, switch, flip. So we're going to keep the first one the same, switch to multiplication, and flip the second one. And now we can go straight across. We can even double check, is there any pre-simplifying? And there isn't. So whatever we get is our answer. So 2 times 8 is 16. 3 times 7, 21. I'm running out of a little bit of space here. There we go. And we're done. Okay, one more time, if I could get thumbs up, sideways, down on the back side of the page, how we're feeling with that, so I just know who to kind of check in with a little bit more. Okay, so at this point, I will come around with a practice test in just a moment. So even if you have not completed your green booklet yet, I would recommend doing the practice test instead. This gives a selection of questions that are very similar to what will actually be on the test. It is a bit longer than what's actually on the test, but just gives you kind of every type of example you might be able to see tomorrow. So just gives you a chance to kind of see, get prepared for tomorrow's big test.